me record before I stop thinking about that. So I'm going to share my screen. Again, here are the solutions to the 2007 number 3. I gave you those yesterday. That was the problem that we should have done in class. So are there any questions on this one? 2007 number 3.
Could we, like, I don't know, go over it? Because I don't know how I kept, wait, isn't that 2007 number 3? Isn't it supposed to be like, wait, because I kept getting the wrong, like, values, and I'm not sure how.
Well, hang on, let's get Fiona in here. Well, so the problem that I think you should have been doing is this one. Is this the problem you were doing?
Yeah, that's the one from in class that I was struggling.
Okay. Hang on, I'm just updating the attendance so that Fiona gets credit for being here. Okay, so A and B, I wrote out pretty clear explanations of why those are true using either the intermediate value theorem or the mean value theorem. So then we can look at C and D. So C, I'll just go up here. So if you want to keep looking at the answers, you can. So for C, W of x is equal to the integral from 1 of g of x of f of t dt, not dx, but dt. Okay. And then you were supposed to find w prime of 3. So to do that, you really have to find w prime of x. So what you want to do is take d by dx of the integral of 1 to g of x f of t dt. Now the fundamental theorem of calculus says that if this up here is equal to x, or whatever it is I'm taking my derivative with respect to, then this whole thing would just be f of x. But that's not what I have. Okay, I have g of x up there. So we need to do a u substitution and let u be equal to g of x. And then what I really want to take is, I'm still looking for dw dx. That's what w prime of x is equal to. And that's going to be dw du times du dx. So I'm going to come down here. W of u is going to be the integral. That's actually not the way I want to write that. I'm going to leave it as w of x is going to be the integral from 1 to u of f of t dt. And in fact, let's just call that w for the moment. Okay. So then dw du is going to be equal to f of u, because that's what the fundamental theorem of calculus says. When I take the derivative of this integral here, I get that integral. And then, of course, I can say from here that du dx is going to be g prime of x. So w prime of x is going to be dw dx, like I have up there, dw du times du dx. So that gives me f of u times g prime of x, or f of g of x times g prime of x. And then if I'm going to find omega prime of 3, that means I have to find f of g of 3 times g prime of 3. Okay, everybody with me? We've been through this kind of thing a couple times where we have to use substitution along with the fundamental theorem of calculus. So that should be getting up into the top of your brain. Kind of the new part here is looking these things up in the table. So the first thing I really want to look up is g of 3. So if I go here, g of 3, whoops, is going to be 4. So this is really going to be f of 4 times g prime of 3, because I have this composite going on with f and g. And then I go back to the table again. Well, f of 4 is -1 and g prime of 3 is 2. So this is going to be -1 times 2, or -2. Okay, so we good? Everybody see where that's coming from?
When we get to the step right below, you take where you use fundamental theorem of calculus, where you get rid of the integral. Why would it be f of b minus f of 1?
Because it's not. Because that's not what I'm doing. So let's go over here for a minute. I just want to put it in a different color. So I've got w is equal to this, f of t dt. Okay. By definition, the fundamental theorem of calculus says if I take the derivative of both sides of this, okay, as long as this and this are the same, as long as the variable that I'm taking the derivative with respect to is the same as whatever I have up here, and the lower limit of my integral is a constant, the definition says that this is f of u. It has to do with how the inverse, it has to do with how the derivative and the integral are inverse operators of each other and they undo each other. But that is a definition. And if you really want to take this to another step, Emma, that may help with what you're confused about, okay? So if I don't take my derivative here, I just do my integral, okay? And I'm going to say that the antiderivative of little f of t is capital F of t, okay? So that when I take df dt, I get f of t, okay? So this is going to give me f, and I'm going to evaluate that from 1 to u, okay? With me? So again, not taking my derivative yet, okay? This is going to give me f of u minus f of 1. Now, f of u is going to be a function, okay? Because u is a variable, and f of 1 is going to be a constant, right? So now when I apply this derivative, I get df du minus what, Emma? When I take, go ahead.
I have no idea.
Okay, I'm taking the derivative of a constant. And what's the derivative of a constant?
0?
Yeah. Okay, so it doesn't really matter what my lower limit here is as long as it's a constant, because it's going to go away when I take the derivative. Okay, and so as I set up here, df dt or df du is going to be equal to f of t, or in this case f of u, because that's my variable. Okay?
Yeah, thank you.
All right. So we good with this part now? Couple different ways to go at it, couple nice little review of the fundamental theorem of calculus. Okay?
Where are those explanations that you had yesterday for A and B? Because that's where I was.
They're gone.
Okay.
You were, I mean, I left, you can go and look at the recording.
Okay. Like when you left, everything disappeared immediately.
Was that when my computer died?
Yeah.
Yes, that was when my computer died. The
Yeah,
recording
so.
is intact, but I
Okay.
did not save that document.
Okay.
Okay?
I have a picture that I can send to you, Jacqueline.
Okay, perfect. Thank you.
Thanks, Emma. Okay. All right, so we needed to talk about part D. Is that true?
Yes, please.
All right, part D. Let me find my notes here. So let's just take a new page here for D. All right, so D says if g to the negative 1 is the inverse function of g, write an equation for the tangent line to the graph of y equals g inverse of x at x equals 2. So if I'm going to write the graph of a tangent line, I'm sorry, if I'm going to write the equation of a tangent line, I need two things, right? I need a slope and I need an intercept, right? Okay, so the slope is the fancy way of saying what?
Derivative.
The derivative. All right, so I am going to let x be equal to 2. I'm going to call that a. Okay. So what I'm going to want to figure out is what negative 2, I'm sorry, that's not true at all. What the g inverse of 2 is equal to, so that I have a point. Okay? And remember that one of the key ideas about an inverse is that we switch x and y. So what this expression is really saying is g of something is going to be equal to 2. Because I want to switch my dependent and independent variables. So that's the first tricky part. So we have to figure out what this question mark is, because that question mark is actually going to go up there. So if we go back to the table, we want to know what value of g is equal to 2. So g of 1 is equal to 2. So that tells me that my question mark here is equal to 1. So this part gives me my point, okay? My point is 2, 1. And then the other thing we need to know is the slope. So this is in your book. It is a tiny little part of your book, but it is a part of your book that you need to remember or you need to know. And it says that if I take the derivative of the inverse of g of A, that is equal to 1 over g prime of A.
Is that a derivative sign? Like
that is a derivative sign.
No, next to the first part of that, like the last.
This is a derivative sign.
Okay.
And this is a derivative
That's
sign.
good. Just wanted to verify. Thank
Nope,
you.
that's okay. Okay. So it's not quite. So then what we want to do here is take the derivative at 2, okay? But that's really, and that should not be the A. That should really be g prime, g of 1, okay?
One instead of 2.
Because this is g of 1.
Oh.
So this is really g inverse of 2 that I'm taking the derivative of. Okay, I am in fact trying to take the derivative of g prime of g, I'm sorry, let me say that one more time. I am trying to take the derivative of g inverse of 2.
Okay, so the point would still be 2, 1, but they would just be switched in the equation.
Yep.
Okay.
Yep. I don't know. I have to change that in my notes because that's not really what A is. Or really what we should probably do is let's just make this a different symbol. Okay. Not at all what I wanted to do. That's what I wanted to do. Okay. So then this is 1 over g prime of 1, which from the table is 1 over 5. And there should actually be another parentheses in there. So this is a good problem because it brings up some stuff, notably this. that doesn't get stressed during the year but could in fact pop up on the AP exam. So then we would take y minus 1 was equal to 1/5, that's the slope, x minus 2. And then if I did my math right, which I did in my head, so I may not have, you can solve that for y. Okay. So it does not surprise me that that is a question that came up. Okay. Any other questions on this? Okay. Then here are the answers to the homework from yesterday, 2013, number 3. Any questions on this?
Can we go over C?
Sure. So part C says, use a midpoint sum with 3 subintervals of equal length indicated by the data in the table to approximate the value of, oh, I'm sorry, I guess I didn't write the whole answer there. So that implies it, so 1/6 of that would be equal to 10.1, I think it's ounces. Was that your question, Sarah?
Can we just go over how you got that?
Sure. Okay, so that should really be what your answer is. I apologize, I had it squared, but I couldn't figure out why. Okay, so we want to use the table, and I only want to have 3 subintervals. So I'm going to go to where I have the problem here. Okay, and I have, if I count how many intervals I have, there's 1, 2, 3, 4, 5, 6. But I'm not allowed to have 6. I can only have 3 because that's what the problem tells me. So I'm going to make an interval that goes from here to here. My second one goes from here to here, and my third one goes from here to here. And I am supposed to use MRAM, which means that when I figure out the height of my rectangle, I use the point in the middle. So if I had a function, and I'm just going to make that function a different color, and it looks something like that, I don't know, but I do know that it's increasing as t gets bigger, then I'm going to take this interval and I'm going to divide it into 3 subintervals. And whatever the value is in the middle of my interval, that's what I'm going to use for the height of my rectangle. Okay, you don't have to draw the picture. I'm just trying to use it so you can see. And so this height here for for my first rectangle here is going to be this value. So that's going to be 5.3. For my second rectangle, it's going to be 11.2. And for my third rectangle, it's going to be 13.8. And then these rectangles are at 2, 4, and 6. So the width of each rectangle is 2. So I'm just going to take 2 times 5.3, 2 times 11.2, 2 times 13.8, and that's how I get my total area under the curve of 60.6. But when I divide it by 6 or multiply by 1/6, what I'm really doing is finding the average over the number of minutes. And so that's why when I take 1/6 of the integral from 0 to 6 c of t dt, that gives me the average amount of coffee in the cup. Okay.
Would the unit be something other than ounces? Could it be integral of ounces?
Nope, I don't think so, because no, because if you think about it, if I just take my integral, then what I'm really doing is I'm multiplying ounces, which is my height, times minutes, which is my width. But when I take 1/6 of my integral, that 6 is time. So that's 1 over minutes, but my integral is still ounces times minutes, but those minutes cancel, and I end up with ounces as my unit.
Okay, thank you.
Okay. All right, so anything else on this problem? Because if not, then we are on to a new type of problem. Okay, we all good here? All right, so we are on to type 6 problems. So type 6 problems are differential equations. So some things that come up here is that you may be asked to find the general solution to a differential equation, and that's the solution that has plus c on it. And what often comes into play here is doing separation of variables, which means that you get all of the terms that have x on the side with the dx, you get all of the terms that have y on the side with the dy, and then you integrate both sides. You might also be asked to find the particular solution. Now, I often talk about the general solution as being like a whole bunch of concentric curves or parallel curves. And a particular solution anchors your general solution to a particular point, which means that we no longer have that plus C, it's plus a particular number, or however that formula works itself out. So when you're dealing with the particular solution, you often have an initial condition. And often what you're trying to do, as I just said, is you're trying to determine what C is from the general solution. You might be asked to state what the domain is of a particular solution to a differential equation. So remember that that's really part of answering the problem, especially if you end up with an x in the denominator or a power of x in the denominator. That solution isn't going to work for 0. Some examples of things that we dealt with were growth and decay problems. And then another big application of this were slope fields. Where you know what dy dx is equal to. And then you may be asked to sketch a slope field, or to interpret the slope field. Or maybe identify the slope field. From the differential equation, or vice versa. And we did some questions like that. There were some multiple choice questions where here are 4 slope fields, here are 4 differential equations, identify them, which goes with which. And finally, you may have to use the slope field or the differential equation to analyze a function, maybe to figure out where the extreme values are, to figure out what the whether something is concave up or concave down. So we've got a couple minutes, and I'd like you to try to do one. So if you look, try to do 2015 number 4, which should be the first one after the multiple choice. I'm not going to worry about the multiple choice today because you've already got, there aren't going to be multiple choice on the test, okay? So if I move this over and move that over, you should be looking at this problem right here, okay? So work on that for 7 or 8 minutes, and then we'll talk about the solution. I'm gonna share my screen so that you can see, check your answers maybe as you go, if you like. All right, so are there questions on what you've done so far?
Wouldn't you just plug in for the slope field?
Yeah.
Because I got, I obviously am just conceptualizing this incorrectly, but because when I plugged in for the point that's like 2, 1, or 1, 2, I mean, sorry, 1, 2, I got 0.
Well,
But,
so
oh no, that works. My brain, oh my God, Jacqueline, I flip-flopped them. Okay.
So I like to make a table that looks like that. This here is a y, so that my x values go across and my y values go down. And then, yeah, you just substitute in and make your slopes look different. Make sure they're angled in the right direction. Okay, I can put in my numbers here if anybody. Leo, you unplugged my charger. Yeah, go plug it in. In there. Oh, okay. It's my pen, sorry. I have that problem. That happened to me in astronomy the other day, sorry. People frequently trip over my cords. Okay, other questions on what you've done so far?
Can we go over part D?
B? Yeah.
B.
B as in boy or D as in dog?
B. Dog.
Dog. Okay. So D as in dog says find the values for M and B for which y equals mx plus b is a solution to the differential equation. So I'm going to have to go here and I want y equals mx plus b. My differential equation is dy dx is 2x minus y. So I know that if I take the derivative here of dy dx, I'm going to get m, right? And that needs to be equal to 2x minus y, right? Because that's what I know dy dx is equal to. So you can do this a bunch of different ways, but effectively what I have are 2 equations and 2 unknowns. I'm sorry, this is part of that equation. So I'm going to substitute in for y. So I've got m is equal to 2x minus mx plus b. And if I bring everything over to the other side, I've got 0 is equal to 2x minus m from when I brought over, minus m minus b from when I get rid of my parentheses. And then I could solve this for x. So I'm going to have 0 is equal to 2 minus m for x. And then left over, I have that. And if this is going to be a solution for all values of x, then each of these little parts has to go to 0 separately. Each of these terms has to go to 0 separately. So this part is nice and convenient and tells me that m is equal to 2. And then I've got m plus b equals 0. But now I know that m is equal to 2. So that tells me b is equal to negative 2. The trick there is knowing that you want this to be true for all values of x. And that means that my terms have to go to 0 on their own always. Okay. So I can see people are still copying, so I'm going to leave this here for a minute. I updated the portal while you were working, and your homework for Thursday is to do that first homework problem for type 6. So that's the 2016 exam number 4. And that is for Thursday's class. I'm going to pop back here for a minute in case anybody else needs to copy some things from here. Are there any other questions on this?
Is C neither a max nor a min because of the critical point at 1? Or what was your way of...
So I know that, so I know that, I know what my values of x and y are at, I know what my values of x and y are, right? I've got x equals 2 and y, which is f of 2, is equal to 3. Okay,
Right.
that's what I'm told. And then I have my equation, dy dx is 2x minus y. So when I substitute in, that gives me dy dx, I believe, is equal to 1.
Oh, okay. So it's just not a critical
Yeah,
point.
it's just not a critical point, so it can be neither a max nor a min.
Okay, thank you.
Sure. Okay, anything else? If you have to go to your next class, please go, but if you still want to ask a question.
How
Hi,
did you
Lauren.
get d2y over dx squared? Like,
Good question. So, Jacqueline, can I go to another screen? Okay. All right. So, that second derivative, by definition, which is actually why it's written the way it's written, this is d by dx of dy dx. Okay, which is something that we ran into a little trouble with the BC stuff when we were doing parameters, parametric equations, although you don't need to know that, but you still need to understand that this is really that. Okay, so that means that I can take d by dx of what dy dx is, and that's 2x minus y. And then I just take the derivative term by term. So the derivative of 2x is going to give me 2. But remember that y is a function of x, so I have to use implicit differentiation. So this is going to be minus dy dx. But I know what dy dx is in terms of x and y. It was the thing I was given. So it's really 2 minus 2x minus y, or 2 minus 2x plus y. And that's going to be my second derivative. Okay, make sense?
thank you.
Sure. Sarah, you good?
Yes, thank you. Have a good day.
You too.